Greetings everyone. We, the students of Electrical Engineering final year, are here to deliver a detailed presentation of our project, which is titled as Symmetrical Components Based Power Quality Event Classification using Classification Technique. Our group number is 18 and our project guide is Professor Ganesh Zadav sir.
Hi, myself Ajay Parasram Gaike. My roll number is 21.
I'm Aliza and my roll number is 58.
My name is Siddhant. My roll number is 59. Motivation of our project. Imagine a world without reliable power. Our modern society depends on electricity to fuel our industries, power our homes, and connect us to the world. But hidden within the complex web of the power distribution lies lurking challenges. That is power quality events. Power quality events refers to disturbances in electrical system that can lead to problems such as voltage sag, voltage swell, harmonics, and transient. These events can cause equipment malfunction, production downtime, and even pose safety risks. It's crucial to identify and classify this event accurately and safely to ensure stable and uninterrupted power supply. And that's where our project comes into play. We are on mission to develop a cutting-edge power quality event classification system that will revolutionize the way we understand and address those events. By harnessing the power of our data analysis, machine learning, and artificial intelligence, we aim to empower engineers, utility companies, and regulators with the tools they need to diagnose and prevent.
So now let us understand the working of our project by understanding every block of the simulation and how they are connected to each other. So firstly, let's understand the main basic programmable system that we have created. So firstly, we create a main basic programmable system in which we start with a three-phase programmable voltage source, which is connected to the three-phase series RL load through the VI measurement block. The voltage source gives supply to the load, and we give the parameters to that voltage source for different PQ events, which are detected by the MATLAB function block further. We measure the voltage VABC, which we get in the go-to block, which is shown here. So from the go-to block, we take a from block from the basic system. Now you can see on the screen the positive VABC. We take VABC from the main basic system and connect it to the DMUX, which gives multiple outputs from single VABC input. Taking these three components, VA, VB, and VC, we take three such subsystems. So let us understand subsystem 1 first. So as you can see, we have given transport delays to VB and VC. And then we have done the summation of these and divided them by 3. Now, VA positive is the result, which is given in the output. Now, let us see subsystem 2. Similarly, in subsystem 2, the delay is given to VA and VC. So, as you can see on the screen, we have given the delay to VA and VC. And now, in subsystem 3, we have given the delay to VB and VA. Okay. So after this, the extraction of sequence components for phase A has been done. Now we got 3 outputs, that is VA positive, VB positive, and VC positive, and connected to the scope. Now we connect these to a square block. These squared values are added to the add block. Then we multiply it by 2 by 3. Here we have used a formula which is also given in the report of our project and also the paper. Then we take the square root and hence we have followed the equation. Now, as we have done it for positive sequence components, we have also done this similarly for the negative sequence components, as you can see on the screen. Then for 0 components as well, we have done the same thing, but here we have not provided any delay to any phase. So as you can see in the subsystem, we have not provided any delay in this. So now we have got the characteristic waveforms of VABC positive, VABC negative, and VABC 0 for each phase. So now let us understand the classifier circuit separately. We use a MATLAB function block to which we give 3 inputs, VABC1, VABC2, and VABC3. So you can see on the screen. Then we created a program for the classification of each disturbance. You will see that on the screen. So this is the program that we have followed. To this, we add a display where values assigned for each disturbance are shown according to the program. So in this display, you will see the values. Now, we use a final scope to which we have connected the positive, negative, and 0 components at VABC along with MATLAB function block output and also the classifier output.
This is the methodology which represents the logical algorithm that is going to be implemented for the classification of different power quality events in our program. So in that flowchart, firstly, the power quality disturbance signal is given to the system. Then it will calculate the instantaneous sequence component as in the simulation. Then it will check whether any of VABC1 and VABC2 is 0. If S, this condition is S, then it will conclude that there is no disturbance occurs in the system and loop goes on for the computing the instantaneous value of the sequence component. If this condition is true, then the duration for which the VABC and VABC2 is non-zero is examined. Then there are the two conditions after that, whether VABC1 is non-zero or VABC2 is non-zero. In this case, VABC1 is a non-zero, then it will calculate the average magnitude of VABC2. Again, there are the 3 conditions for the identification of basic power quality events. If first condition is that if VABC1 is less than 0.9, then it will say that it will side. If VABC1 is greater than 1.1, then it will show the swell interruption. If VABC1 is greater than 1.1, then it will show the swell power quality events. If VABC1 is less than 0.1, if VABC1 is less than 0.1, then it will show the interruption of power quality event. Now, in this case of VABC2 being non-zero, again there are the further conditions. Then it will calculate the average magnitude of VABC2. Again, it will check VABC2 is greater than 0.01. Then if this condition is true, then there are the 2 conditions. If the classifier shows y equal to 4, that is the classifier output, which will show the continuous for the duration of event, then it will conclude to be it is harmonics. If y equal to 4 is not constant during the whole duration of power quality event, then it will conclude that it will high frequency harmonics has occurred. If VABC2 is greater than 0.1, then if this condition is false, then it will conclude that there is no disturbance occurs. So it will show the y equal to 0 as classifier output.
The implementation of simulation prototype has been done using MATLAB Simulink. Results of different power quality events at various disturbances has been observed. So for the first power quality disturbances, that is sag, it can be seen that a fault has been occurred from the duration of 0.2 to 0.4. So in VABC, it can be seen that the waveform there has been altered. In VABC positive, it can be seen that a sag has been occurred from the same duration. VABC negative is considered as the reference value, and VABC 0 is 0 for the whole time. And as from the 5th waveform, it can be seen that the power quality event classification has been done. So the sag is valued as 1. So 1 has been shown. Similarly, it has been done for 40% and 60%. As for the second power quality event, it is swell. It can be seen that from the waveform VABC, from the duration of 0.2 to 0.4, the waveform has enlarged. That means a swell has occurred. For VABC positive, it can be seen that from duration 0.2 to 0.4, the swell has been occurred. For VABC negative, it is considered as the reference value, and VABC 0 is throughout. From the fifth waveform, it can be seen that power quality is at the second level because swell is defined as second. Similarly, it has been done for 120%, 140%, and 160%. The next power quality event is interruption, as it can be seen from VABC that an interruption has occurred from 0.2 to 0.4. Here, the supply has been shut down or cut off. From VABC positive, it can be seen that the waveform is nearly above 0. From VABC negative, it is considered as the reference value, and VABC 0 is throughout. From the fifth waveform of PQ event, it can be seen as interruption has been defined or valued as 3. So 3 has been occurred. The next power quality event is harmonics. It can be seen from VABC that the harmonics has occurred from 0.1 to 0.3. From VABC positive, it can be seen that a distortion in the waveform has been occurred. From VABC negative, it can be seen that a lift in the waveform has been occurred. And VABC 0 is 0 throughout. From the power quality chart, it can be seen that the waveform level is on 4 as the harmonics is assigned value of 4. Similar to the last power quality event, this is high frequency harmonics, as it can be seen from 0.1 to 0.3 in VABC that the waveforms have enlarged. In VABC positive, negative, and 0, the waveform is constant throughout. The only difference here is the power quality classifier detects it in the start and the ending. We have successfully completed the classification of different power quality events. There are various ways in which this system can be further improvised. The project represents a modern but a simple approach to detect power quality events. And the learning outcomes are we have understood the characteristics of different power qualities event that can cause disturbances in the power system. We use MATLAB simulation to implement this project, and we completed various courses on MATLAB for a better understanding of the functions.